Thank you. So first, I'll tell you what a knot is. A knot is this. It's an embedding of the circle in 3 dimensions, or some other 3-manifold, but you probably don't know much about manifolds at this point in your career, so I'll just say 3 dimensions. So the thing that we usually talk about is S3, so it's like R3 with all this stuff around us, but then there's this other point at infinity that pulls all of the ends of R3 together, which is weird. So you can just think about it as in 3 dimensions like that. I forgot to get my notes out. Is this on? Okay. Okay, so here's a 3-dimensional knot. This one's called the Truss Oil. So I'll throw this at you so you can play with it. I'm gonna press some buttons until something happens then. Is that? That's good? Okay. So this one's also the Truss Oil. Throw that one at you too. This one is the figure 8. He's going to come up later too. So you can mess with that one. And this one is those two are of the same type. They're called twist knots. This is a twist knot also that has, let's see, 1, 2, 3, 4, possibly 5 crossings, I'm not sure. So here's an empty, or just a rope, So it's a string. We can glue the ends together like I did with those. So this guy's called the unknot. But you could do crazier things. Say something like that. That might shake out to be, it shakes out to be the Truss Oil. But, so I have all these ropes, and I'll let you play with those and see what knots you can make. So if you get bored, you can just play with some rope. Okay, so those knots are in 3 dimensions, and usually when we draw knots, because it's hard to, the knots that I work with have like 90 crossings or more in them, so it's really not possible to make them out of rope. So what we do is project the knot onto a plane. So that will give us, so here's my knot in three, or here's a 3-dimensional thing. Oh, I'm gonna mess it up. It's living in 3 dimensions. So whatever it looks like in 3 dimensions, I take that and I push it back into a plane. And then so push into a plane. And then what you get is something that looks like this. So you have these things called crossings where, because it was in 3 dimensions, you couldn't push it all the way into the plane, and you have to jump over another strand that you did push into the plane. So these things are called strands. I think the definition is kind of just from one undercrossing to another is a strand. So and then we have these bits, which are called crossings, and they're where strands meet, so it's kind of a circular definition. But I think you probably get what I'm trying to say there. So you have crossings and strands. And so that's where the idea of coloring is going to come in, where we're going to color the strands, and the colors will meet at crossings. So So a way to tell knots apart, or So a way to tell that knots are the same is to do Reidemeister moves. So maybe you've seen this before if you've seen a knot about talks or talk about knots. So the first type of Reidemeister move, ooh, this is where the ropes would be useful. I need 3 ropes, and thank you. Okay. And 1 other person. So if I could have 1 person come here. So this is a Reidemeister 1. There's this guy. Yeah, come. So hold this for me. So you take so here's a straight part of a knot. There's knot out there. So you take this string and you go like that. So basically you just take some bit of the knot and you make it twisty. You just put an extra twist in it, or you take a twist out of it. So another way, and this is the Reidemeister 2, just stay right there, Emily. You take 2 parallel strands of the knot and you cross one over the other one. So that corresponds to this. So you can do this or this. Okay, so that's a Reidemeister 2, like that. And then a Reidemeister 3, so both of your hands are going to have to get involved. So you take 2, let me draw a picture of it. I'm just leaving you there. You take 2 strands that are crossing, and you have this other strand that crosses. And that's the same as if I take this strand and move it up across the crossing. Okay, so I may need another. Come here, Alec. Okay, so you hold. Here, I'll give this one to you, and this one to Emily. Alec. So I'm going to take this and turn it into this. So in 3 dimensions, that's pretty easy to see. You just go like this. And as long as nobody gets in your way, you can do this all day long. Okay, excellent. Let's have a hand for Alec and Emily. Oh, and here you can have the ropes back to play with now. Okay, so you can take, I always draw the Truss Oil this one certain way because I always get it wrong if I try to draw it the other way. So this knot and this knot are the same. So I would like you to take 2 minutes and try to find a series of Reidemeister moves to get from one to the other. There are infinitely many ways to do it. Oh, and you have 2 copies of the rope Truss Oil, so. This is also the knot that you tie into your shoes if you tie your shoes. Okay, does anyone see a good place to start? Okay, well, okay, so what I would do is, this is just, there are infinitely many ways to do this, so it's not. I would move this down, so let's see, show you an isotopy. So I would move this strand down to get closer to that guy. Now I'm going to do a 3 on these crossings. So I'm moving this across here. So I get this. Okay. Now I have this little guy. So what do I want to do with that? Pull it taut, so it's 1 there. Okay. I haven't done this in a million years, so I don't remember if this is a good way to go.
It's done.
Is it done? Show me.
Just slide the bottom loop up. You're looking at it to 90 degrees to the left.
Oh, I want to move my head right then, right?
No.
Okay.
No, it's not done.
No, not yet. So now, this thing is the thing you have issue with. So let's do something with that. Let's move it. I fear I'm just making a smaller trefoil of the same shape. So I'm going to swing this whole guy. Oh, that'll be it. Okay. So I swing this whole bit over so that it, and this is a whole mess of Reidemeister moves of 2s and 3s. It goes like that. And now, oh, that first 3 I didn't really make sense. So do you see what to do now? So you take this little guy and you move him back this way. And we're done. So that was all Reidemeister 2s and 3s, but that's in practice how you would actually use them. You just sort of move the knot around, and you don't think about what the 1s and 2s and 3s are. You just do it. So we showed just now, knowing almost nothing about knot theory, that those 2 are the same knot. So that's fantastic. We can do that really quickly. And I've been doing knot theory for a long time, and you were just as good at it as I was there. So how do we show that these 2 knots are not the same is where we're going today. So this has got 3 crossings, that's got 0 crossings. I could play with that one, do Reidemeister moves all day long, and I would never get this guy. But how do I know that I can do one more Reidemeister move and get to this one? Or some finite sequence of my Reidemeister moves and get this one? So that's where Reidemeister moves are kind of bad, because they're easy to show if you find 2 knots are the same, but to show that 2 knots are different is just basically impossible with Reidemeister moves. So that's why we're going to talk about coloring. Okay. Okay, so a knot is called tricolorable. if we can color the strands, literally color them. So that at every crossing, all colors are the same. Or all colors are different. Okay, so let's see an example of what that means. So let's look at that guy, the Truss Oil. Oh, and I should say that a coloring that only uses one color is called trivial. So I know that many of you are math majors, and a coloring, well, trivial is the secret math code word for this is not interesting, let's not talk about it. So we're not really looking for trivial colorings. We want non-trivial colorings. So we have red, blue, and green chalk. So I'm going to color this strand blue, randomly chosen. Okay. So I want a non-trivial coloring. I'm going to color the other two crossings there, or the other two strands that come into this crossing. One of them will be red, and one of them will be green. Okay, so this is a pretty simple example. So if I look at this crossing, I have one blue, one green, one red. If I look at this crossing, I have one blue, one red, one green. If I look at this crossing, I have one red, one green, one blue. So that is a valid, non-trivial 3 coloring. Okay? So what about this one that we wanted to say was different from that one? Does it have a valid, non-trivial 3 coloring? No, because it's only got one strand, no crossings. So we can only color it one color. What color would you like to color it? Red, okay. So this guy is not really interesting. He's just red. And that's no fun. Okay. So let's look at the color, the knot that was on the poster is this guy. Who made the poster? Oh, well, it was a wonderful choice of knot he made. So I can take this coloring from this knot. So I have this strand is green, and this strand is green, and then I have red and blue. So what's a way that I could color this so that it's a non-trivial thing? Sorry? I can do that. I can say, okay, well, this is green, so I need a red and a blue, so I'm going to call this one red. And this one is red and green, so this one has to be blue. And hey, look, everything worked out nicely. I could also have colored everything green over here, and that would have been fine. That's a valid, non-trivial 3 coloring. So that actually happens all the time. If you have a 3-colorable knot and you break it somewhere and add any other knot onto it, then it's still 3-colorable. So you can do that. So this guy is called the granny knot. It was a good example because I could split it in half and each one has a valid 3-coloring. But even if this one didn't, I would still have a valid 3-coloring of the whole thing. Okay, so I want you to color. What fun would it be to come to a talk about coloring and not to color yourself? So I want you to try 2 knots, actually. I want you to try this one. And I want you to try this one. Okay, this one's really hard to draw. I think that's right. My own personal name for that guy is the monster. There is an actual monster knot, so if you said that to anyone else, they would not know what you're talking about. But I call that one the monster because it was the first knot I met that I could not draw no matter what I tried. So I will not think less of you if you can't draw that one. So try coloring those things. And if you don't have colored pencils, just, label them R, B, and G, or whatever the letters corresponding to your favorite colors are. I have no idea.
It's got like 2 years or something.
Yeah, the thing about knots is they have a basis in reality, so sometimes they're called weird things.
Yeah. Is the monster not associated with the monster group in any way?
It might be. It's got like 700 crossings or something. Not that actual monster knot. But
Are they?
I have no idea.
They're probably both just suck.
So if you're having trouble drawing that, one thing to remember is that the crossings go over, under, over, under, over, under. So if you're having trouble, that might help you. You may have to edit this out of the video. It won't be as interesting.
Yeah, we should have played Jeopardy music on the microphone.
I could sing. Don't Google that. Did you get a 3 coloring for this one? You couldn't find one? No, good, because it's not 3 colorable. You shouldn't have gotten a 3 coloring for this one. So, because you only have 3 colors, it doesn't matter which one you pick. So we pick green. I'm going to do this strand in green. So you just pick a crossing. So here's a crossing. I'm going to choose this strand to be red and this strand to be blue. So this is how you show there's not a 3 coloring. So based on the information at this crossing, what color does this other strand have to be? Blue. Based on the information at this crossing, what strand should it be? Red. And based on the colors at this crossing, what color? Green. So this, in order for this to be a valid 3 coloring, this knot, or this strand of the knot, would have to be all 3 colors at once, which is silly. That's not so. For those of you in my discrete math class, that's a proof by contradiction that this is 3 colorable. Okay. So, did you find a 3 coloring for this one yet? You got one? Okay. So this is how I did it. I just pick a strand. This is pretty much how it goes when you're coloring things. Pick a strand, pick a color, color it that color. Now this crossing, so I pick a crossing at random. I pick a strand at that crossing. I color this one red and this one green. And from there, the knot will tell us what to do. So we have green and blue at this crossing, so that other strand has to be red. We have red and red at this crossing, so what do we do there? Red. Okay. Here we have green and red, so this guy has to be blue. Okay. So this crossing tells me the last strand has to be green. This crossing tells me the last strand has to be green. And this crossing tells me that the last strand has to be green. So there's no conflicting information. We just color it green. And there we go. So this guy is fun because he has a crossing that's all the same color, but all the other ones are different colors. I don't think you actually have to use that crossing to be all the same color. Once you know there's one, I think you can just pick one and go from there, but I'm not sure about this particular knot, if that's true. I just think that might be true. Okay. So the reason we would do this is because knot coloring is let me say it this way, tricolorability is a knot invariant. So what I mean by that is if I have this knot and I do any sequence of Reidemeister moves to it, it's still going to be 3 colorable. And if I have this knot and I do any sequence of Reidemeister moves to it, it's never going to become 3 colorable. So I can't do Reidemeister moves and make it not 3 colorable or 3 colorable if it was already 3 colorable or not 3 colorable. You may have to write that sentence down to figure out what it meant. So if you're bored, try that. Okay, so let's prove this. This is most of a proof. It's proofish. So the first Reidemeister move we said was this. Okay, so I'm going to pick green, say, and I have a bit of a knot. So the ends of this knot are connected to, or the ends of this little bit are connected somewhere else to the knot. So what comes in has to be green and what goes out has to be green. So I created this crossing and both ends of it have to be green. So at this crossing we just have a crossing where all of the strands come in the same color. So that one's pretty easy. So suppose instead I have this guy and it goes to this guy. So if both of these strands were green, then they're both still green, and nothing interesting happens with the coloring. But say we had a blue one and a red one. So this guy is still going to be red because the ends have to be red. Now here I have a blue end there and a blue end there. So this crossing tells me the little bit in between has to be green. So when I do the Reidemeister 2 move, I get a little extra green bit in my knot. So that's fun. The 2 actually does something. The 3 has a crazy number of cases, and we're not going to do all of the cases. I'll just show you one of the cases. I'm not sure I know which case I chose. Okay. Okay, so here's my Reidemeister 3. I'm going to call this one, to actually do the Reidemeister 3. So, over, under. Okay. So, this one coming in is green, and this one coming in is red. So the reason there are so many cases is because you can choose the ends of these to be a lot of different ways. You could choose the whole thing to be all the same color. So this one's got to be blue. So here's where the choosing cases can happen. So say that one's green. So this one must be red, and this one must be blue. Right? You see any mistakes? Okay. So now this one coming in had to be green. Oh no! This one still is going to be red. This one's still going to be blue. And this one's still going to be red. And this one's still going to be green. So this crossing tells me this little guy has to be green, and this crossing tells me this little guy has to be green. So that's just one case. There are lots of those. I think you're all smart enough to do it. So, but the main thing here is that tricolorability is a knot invariant. So I can put all of my knots into 2 buckets. I have the bucket of non-tricolorable knots and the bucket of tricolorable knots. So that's a pretty good thing. I can show that this knot is not, I don't remember if I said this is the unknot. So this knot's not the unknot. This knot might be the unknot. I don't know. This one's definitely not the unknot. That one's definitely not the unknot. So what do I do then about this guy? Because he still might be the unknot. Okay, so the thing I'm going to do is to generalize the idea of 3 colorable. So, does anyone not know about modular arithmetic? Have you all figured that out at this point? So, good. That seems... So a knot is n colorable for some positive integer n. If x plus y is congruent to 2z mod n. So I'm talking about x, y, and z, and I haven't told you at all what that means. So here's a crossing in a knot. This is z, this is x, and this is y. So what we're doing, the coloring, the actual using colors, is just a metaphor for labeling the strands of the knot mod n for some n. Okay, so if we look at this guy. So we know he's not 3 colorable. We know this one's not incolorable for any n. Not, I guess, non-trivially incolorable. And I'm not even going to get close to proving that this is not invariant, but it is. So that you'll just have to believe me on. So if this knot is n-colorable for something, then it's different from the unknot. So we're going to go with 5. Okay, so I'm going to call this strand 0 because it doesn't matter. So what I need here at this crossing is x plus y congruent to 0 mod 5. So what are 2 numbers that if I add them together I get 0 mod 5? 3 and 2. So I choose this one to be 3 and I choose this one to be 2. So here at this crossing I have 0 plus, say, y is congruent to 6 mod 5. Well, 6 is just 1 mod 5, so 1. So what does y have to be? It has to be 1. Okay, so I have 0, 2, 3, and 1. And here, so we just want to check 0 plus 2 is congruent to 2 mod 5. Good. And 3 plus 1 is congruent to 4 mod 5. And that one's also good. So all the crossings check out, and we have a 5 colorable thing here. So this guy is 5 colorable. Since this doesn't have a non-trivial 5 coloring, we're good. This is definitely different from the unknot. Okay? So here's a fun one for you to try. Oh, I'm not going to draw this well in chalk. So try a 5 coloring of that. And then I'll have I'm just going to go with that guy is called the Stevedore Knot. This is a word that I learned only because I did knot theory. A stevedore is a person who, I guess probably typically a man who at a dock lifts and moves giant boxes with rope. So the Stevedore knot is the knot that they tie because this knot does not slip out of rope very easily. So that's why this is called the Stevedore knot. That's a fun fact. So try to find a 5 coloring of those. Am I supposed to talk until pizza comes? What? Okay. Is that clock right?
I think so.
Okay. Where's your time? Okay.
You have a Mac or something.
Yeah.
But I started according to that clock, so just go ahead.
Okay. I suspect you should have, but it's been a long time since I tried. I just sort of was like, I'll try this one. So let's call that 0, shall we? So here we need x plus y congruent to 0. So what x and y do you want to choose? What's that, Alec?
1 and 3.
1 and 3? We're doing a 5 coloring. 1 and 4 is what you choose? Okay. So we choose 1 and 4. So here this crossing will give us information. So we have 0 plus y is congruent to 4. 8, which is 3 mod 5. So what is y then? 3. Okay, so here at this crossing we have 4 plus y is congruent to 6, which is 1. So what is y? 2. Here at this crossing, now we must have, so this one's already decided, so we just need to check. 1 plus 3 is congruent to 4. That's true. And here at this crossing, we have 0 plus 2 is congruent to 2. Good. I circled the crossings so that I made sure I checked them all. That's just why I'm doing that. Okay, so did you find a 5 coloring for this one? I honestly have no idea if it's 5 colorable. I don't remember. But we can see what happens. So we have 0. Again, oh, this is an undercrossing now. That could be bad. 0 plus y is congruent to 2z. Let's not do that. Let's go for this crossing. So we have x plus y congruent to 0. So do you want 1 and 4 or 2 and 3?
2 and 3.
2 and 3. Okay. So let's go to this crossing. We have, oh, we don't have enough information there yet. We have to go down the line here. So we have a 0 coming into a 2. Let me erase that guy. So we have 0 plus y is congruent to 4. So that tells me this one has to be a 4. I have 2 plus y congruent to 8, which is 3. So y has to be 1 there. 4 plus this is congruent to 1. So this has to be 2, right? 2. 4 plus this is congruent to 2. So y then has to be 3. Yes. I've lost my ability to add entirely recently. So it's okay, so I have a 3 here, and a 3 here, and a 0 there. So that's bad. So that doesn't work. So that's one case that we just started with a 0, then our 2 options here were 2 and 3 or 1 and 4. Those are the only possibilities. It doesn't really matter which one we choose, so we have to try again. If I can draw this knot again. It's not as pretty this time. But. Okay, so I chose 0, and now I'm going to choose 1 and 4. I can go through all this again. So this has to be 0, that one has to be a 3. This one then has to be we have 4, 6, so that has to be 2. We have 3 and 4, so that one has to be 1. And then here, I have 1 coming into 1, so this one has to be 1. But then at this crossing, I have 1, 1, and 2. And that's a proof that there is no 5 coloring. Because I started with randomly choosing 1 to be 0, and that's fine, you can do that. It doesn't matter which label you choose. And then from there you have 2 options, 2 cases that you have to deal with. Neither of them work. Yes?
Why do you only have 2? Why couldn't it be 4 and 2 instead of 4 and 1 and 2?
4 and, sorry.
Instead of choosing either 2 and 3 or 1 and 4, why did you not choose 3 and 4?
Because it has to add up to 0 mod 5. So your ways to add up to 0 mod 5 are 1 and 4 or 2 and 3. So those are the only 2 cases. That's why it's a good idea to start at 0. Although you will only have 2 cases either way. It's just 0 is nice. Yes?
How do you know switching the 1 and the 4 wouldn't make a difference?
They are... I'm certain that's true. But they are... the labels don't really matter. They're just sort of... So you're either going this direction around the circle or this direction around the circle. So because mod 5, 4 plus 1 is 5, you're not buying that. Okay, let's do it. Oh, I can't draw this knot again. I promise it works. Is that okay? Okay. Ooh, that took a lot of time. Okay, so now in our bucket, we have 3 buckets. We have not 3 colorable or 5 colorable. We have 3 colorable. Oh, we have more buckets than I thought. Some knots might go into more than 1 bucket. We have neither 3 colorable or 5 colorable, 3 colorable, and 5 colorable. So obviously there are more buckets than that. But then we'd have to figure out if the Truss Oil is 5 colorable, which I think it is. Okay, so this is not a great invariant of knots because you have a bucket of 3 colorable and a bucket of not 3 colorable and a bucket of 5 colorable and a bucket of not 5 colorable. But it works at a very basic level of, I know in my soul that this knot is not the unknot, but I had no way of proving that until I talked about coloring the knot. So for fun, easy knot theory, it's a really useful thing to do. And you get to use pretty colors. So everybody wins there. But you can actually do a lot more complicated things with this. So drawing this, it's not a very pretty one. I'm going to draw this guy again. So the definition of end coloring that I gave you actually will work for 3 coloring because it's mod 3, so at every crossing you have to use all of 0, 1, and 2. So it just works out nicely every time that it's that way. So a way to do really cool stuff with this is to determine or define determinant of the knot. And the way we do this is we associate a matrix to the knot. And every crossing has a row in the matrix or a column in the matrix. It doesn't matter. So at this crossing, we're going to call this crossing 1, this crossing 2, and this crossing 3. Okay, so I've apparently chosen columns. So you follow the knot around, and you come to this crossing. And at this crossing, this strand is over. So at crossing 1, I put a 2. Then I keep following the knot. At crossing 3, I'm under, so I put a 1. And then at crossing 2, oh, that shouldn't happen. Oh, wait. At crossing 2, I'm over again. This knot is alternating? I think I went the wrong direction. Okay, anyway, I think that's a 2. Okay, so then I keep following, and then I have a 1. I think I did this wrong. I think it goes instead like, so this strand is...
I think that top one's supposed to go on your right should go under, on the left should go up.
Sorry? Okay. I think that's okay. So apparently I forget how to do determinant. Did I write this down? No, I didn't write it down because I thought I knew how to do it. Okay. So in this crossing, I have, say this is strand 1, strand 2, and strand 3. This is how I do it. So 2 is over in crossing 2, crossing 1 rather, and the other 2 are under. Then this guy in crossing 2, strand 3 is over, and the other 2 are under. This is how it goes. And then in crossing 3, strand 1 is over, and the other 2 are under. Now, if you took the determinant of this matrix, you would get 0. So you just drop a row and column. I think there might have been, okay, so what I have left is 1, 2, 1, 1. Well, this one's not going to be interesting because its determinant is -1. So the determinant of that is equal to -1. So that's more or less how you calculate the determinant. This guy turned out not to be that interesting because the determinant is -1. But there's a neat theorem that I worked on when I was an undergraduate. So it used to be a conjecture, and so I think of it as a conjecture, but it was proved last summer. So it's now a theorem. But what it says is, if a knot has prime determinant, P, a P crossing of the knot uses one color, let's see, exactly the number of crossings, number of colors. A P coloring, yeah, thanks, David. That was David, right? A P coloring of the knot uses exactly the number of colors as crossings. And I didn't really say this, but a knot has exactly as many crossings as it has strands. So that means every strand in the knot uses a different color, which makes it very pretty. So that's sort of the most exciting thing I know about it is that if you're coloring with P colors and you have determinant P, then you use all of the colors. This guy had determinant -1, so I couldn't, I did not demonstrate that well for you. I think this one should have determinant 3, but it's possible I don't know how to do the determinant. So look that up on the internet. Ask the internet how to do knot determinant. Like I should have done earlier today. Okay, I think that's my time, so I'll shut up now.
Does anyone have any questions for the speaker?
You discussed having non-trivial color schemes, or if it's a 3-color knot, and it's non-trivial